This YouTube covers a more in-depth look at formatted input and output streams that we've been using all along in this programming class, but we're now just going to take a more formal look at it. This is not a difficult chapter. There's a lot to be learned about formatting your input and output, which will be really important when we do files in another chapter or so. There's no substantial programming examples in this chapter, and no substantial programming assignments either. But come back to it, reference it when you need to use it. This is kind of a breather chapter for you. And you know I like putting little pictures in the beginning, and since we're talking about streams, I have an illustration of a subtropical jet stream which affects our weather. But what are streams really? So streams are really, in terms of C programming, it's our input-output data streams that right now we're sending either to our monitor or getting from our keyboard. So those are serial streams of data that we're sending to and from those locations. The serial stream, input and output in C, is actually independent of the piece of equipment involved, such as the keyboard or display. So I could stream instead to a printer, or I could stream to a file, which we'll do later on. C has 3 predefined standard streams that are automatically available in every program. These are the standard in, the standard out, and the standard error streams. Both standard in and standard out can be reassigned so that you're outputting or inputting to and from files. So let's look first at output to the screen, which we've been doing all along with our printf statement, but we're going to formalize our look at the printf statement and probably learn a few things about it. So printf is a function for sending formatted output to the standard out stream, and that's the way you need to think about it. And our output is always formatted. There's also a more secure version of the printf statement called the print_f function, which is more secure mostly because it doesn't permit this %n specifier, which I think I cover in a few slides. It's really allowing you to have a no input. So we're used to this. This is the formal function prototype for the printf statement or printfs function. This is the formal function prototype that you would find in the standard IO library. And this is kind of a usage type statement saying we usually put some kind of a format control string in here, and then we have some other arguments that can substitute in. When I looked at your textbook, I was not real thrilled with the examples given. They were there, but I think I like to put things in a little bit different organization. So I decided that this chapter is many of my own examples. So it is going to be complementary to your textbook, which is chapter 9, and I am covering the same material. I will be in particular taking some material from this textbook, beginning C, which I reference from time to time in these YouTubes. This is a free ebook from www.itebooks. Right here, there's a link. It's a very thorough C programming book. I may actually switch to it in future teachings of this class. So I'll be using it because I like its presentation of this particular input-output chapter. So let's go back to printf, which is outputting to the screen, and let's take a formal look at it. So when we have an output specifier in our printf command, our printf function, you have options that you can put in it. And so this is the general form of the format specifier that's the argument of a printf function. It always begins with the %sign, so that's the start of a format specification. And then I have these other options here. I can have flags, field width, precision, a thing called a size flag, and then finally the type, the data type that we are sending to the screen. And there's a whole list of them, many of which we're familiar with already, and some which we haven't really used. So I'm going to be going through each one of these options that you can put and looking at some examples. So let's start with the flags. So it says flags can be a minus, plus, space, a hashtag or a £, or a 0. Looking at the flags. So if I put a plus after the percent sign. It ensures that there's always a plus or a minus sign just before you output your value. So you can have negative, you can have positive. If I have this flag, a minus sign flag, that makes our output be left justified. If I have a 0 here, that means I'm going to be right justified, but I'm going to just pad the output with zeros. And then I have this, some call it a pound sign, some call it a hashtag, but it ensures that you are going to put zeros in front of an octal output, or 0x in front of a hexadecimal output, that a floating point number will contain a decimal point, or if you're using the G floating point conversion, that you trailing zeros will be admitted. And a space, if you have a space there, it specifies that positive or 0 values are preceded by a space rather than a plus sign, so the plus sign won't get printed. So here's my example. I used each one of those flags in this example. In each case, I wanted to print the number 15, an integer 15. Here the plus sign is there. Plus sign means, plus sign means there's always a plus. I chopped it off. There's supposed to be a plus sign shown. I better rerun that example. Voila, I reran the example, and you get the results here. So I'm right justified here with the plus sign printed. The minus sign makes me be left justified. The 0 puts leading zeros in. By the way, that only works with a decimal specifier, doesn't work with an integer specifier. The space means it's right justified, and I will not put a plus sign in. I will put a minus sign if it's there, but I will right justify it and not show a plus sign. And if I have this last one, this is a hex number, and I will print it out as a hex number. So 15 has this prefacing part in it that says that this is a 15 hex, and I want to print it out as hex. I want it to indicate hex, and so that's what the flag will do for it. Here's some examples about field width. Field width is next. Let's go back here. So I covered flags. Next is field width, which is the maximum number of characters in the output field. So field width. I have an example here again using the number 15, but I changed my field width to a 9, kept the example the same otherwise. So I have 9 spaces with which to put my answer in. Right justified, left justified, right justified with leading zeros, right justified without the plus sign, and right justified as a hex number. Notice these are all aligned, so my sign here and my 0x, they are counting as part of my 9 characters that I'm allotting for the printing. The next option you have is a precision. Notice it's a dot precision. So let's do an example of that. So here's an example. I'm giving my field width as being 9, and then I'm using long floats because this is about precision. But so I have 9 with 0.1 precision, 0.2, 0.3, and then a few other playing games with the flags in the front here. So I'm doing 10 divided by 6, which is 1.6666666 forevermore. If I do not specify a precision, I default to 6 numbers by default past the decimal sign. But this one I have 1 digit of precision, so it rounds off, and you can see 2 digits, 3 digits is right here. This is 3 digits left justified. This is 3 digits right justified with leading zeros, and this is 3 digits right of precision right justified without printing a plus sign. And in all of these cases I gave a field width of 9. The next category was the size flag. I've actually never used it formally in a program, but I'm sure it has its use. I played with some values of it right now, but it looks like it modifies the meaning of the type specification, is what it says. And so it gives you some very specific examples. One of them includes the size t. So if I say z, and I'm talking about a size t, then you can have the following conversion specifiers with it. I just tried one here. I used the h. H specifies that these type values will apply to a short or unsigned short. And so it actually, what it ends up doing is it prints that that's what it's applying to the number. So it will print that specification there. I'm not going to give you any homework with size flag. And then type. A lot of these we're already familiar with. We're going to print a decimal or an integer, unsigned, octal, and there's a bunch of examples here that I thought this was the most thorough chart that I can find. The /n is nothing is printed, or %n means nothing is printed. Print f_s does not allow this. There's some security issues with that. This chart came from this website up here, www.c++.com, reference. It applies to both C++ and C. Notice that one of the things we haven't used too much, but we are when we do some file operations here in another chapter, is using exponential notation. I have mentioned it previously in some other chapters that you can specify a number, print it with an exponential type notation, meaning this is 3.9265 times 10 to the second power. And you can use upper or lower case. That's just a personal preference. It makes no difference. Same thing with specifying a hex number. I can specify them with upper or lowercase hex digits, your preference. Let's look at collecting input from, in this case, our keyboard. Now we can get input by reading from a file as well, which we'll learn about soon. So we've been using the scanf. There's also an scanf, but we're just going to talk about scanf right now. They're very similar. And it always starts with the format specifier, and then I have some similar options here, and there'll be some arguments here, like what the thing that you scanned in, where you're going to put it, the address of where you're going to put it. So once again, a format specifier always begins with a %sign. We have something new here, an asterisk, which in this case, in a scanf command, means that the input value is to be ignored. I will show you that by example. Again, we have a field width. Again, we have a length modifier, which I'll talk about in a moment, and then a conversion character. Actually, I'm not going to talk about the length modifier. And then what kind of data type that we're using when we get our input from the keyboard. Actually, you get the input from the keyboard, but then you can save it as a certain way. So that's really a conversion type specifier. So let's go through each one of these. Let's start with using that asterisk right there, right after the %sign that starts our conversion, our format specifier. This asterisk sign indicates that the input data item corresponding to this particular format specification, meaning corresponding to the thing right after the %sign, should be scanned but not stored. For example, if you say %*d, it will scan an integer from the keyboard, but it will not store it anywhere. And here's a very specific example. I ask the user to enter a date in this format. So the user is going to enter 11-08-2016. And so I'll use the scanf to collect his input. But look at how my format specifier reads. It says I expect an integer. That will be the month. And then there will be a character, but ignore it. So I have a *C. There'll be a character, ignore it. Don't do anything with it. Then I get another integer. That must be day. Then I get another character. That's a dash sign. And then I get the last integer, which is the year. And so I'll save an integer into month and an integer into day and an integer into year, and I'll discard the two dash signs in the usage of the scanf function. So pretty nifty. Next is the width option. Specifies the maximum number of characters to be scanned for this input value. But if there is white space found before the width, the entire width has been scanned, then the white space is going to indicate that that's the end of the input. So I have two examples to show you. In one case, I asked the user enter a 6-digit integer, and then my format specifier says get 2 digits and then get the rest of the digits. So %2d means get 2 digits, store it in X, and %d means get the rest of them and store it in Y. And then I have a printf statement. So the printf statement shows what the result is. So ran the program. I entered 1, 2, 3, 4, 5, 6, and sure enough, 1, 2 went to X, 3, 4, 5, 6 went to Y. But that's not showing what happens if a white space is involved. So I reran the example, and I said enter 10 digits, and I gave space for 10 right here, and I'm going to store it in X. But when I entered my 10 digits, I entered 0, 1, 2, 3, 4, 5 space 6, 7, 8, 9, 0. And what I got stored for X was 1, 2, 3, 4, 5, and because it encountered a space, that was the end of the scanf, collecting the digits. Even though I said collect 10, it doesn't collect the space. That space means the end. Here I print what the type. Oh, I skipped the size flag. We're not going to use it, and I went on to type. So type is a lot of the types that we're already used to. You get a scanf, you say stored as an integer, you say stored as a character, you say stored as a double. Many of these we're already used to using. So this is just a summary of almost everything that we've been using. The only difference is, well, for example, if I get it as an exponential with either E's or F's, then I can enter my number from the keyboard as 2.76 E minus 3, for example. So it allows me to enter very large numbers with exponential notation. So examples. Various examples here on the type. Here's my example 1. I want 7 integers, and I'm going to store them in A, B, C, D, and E. But then the user is entering them as integers. The user thinks he's entering integers. But when I store it, I'm going to store A as a decimal. That's a D. I'm going to store B as an integer. I'm going to interpret, I should say. I'm going to interpret C as an octal number. I'm going to interpret D as and store it as an unsigned integer, and I'm going to interpret and store E as a hexadecimal number. And then my next thing says display the results. So, and I showed it all as decimal, but remember I got the 5, it should be 5, there's 5 there, not 7. I got the 5 integers, but I stored them different ways. I stored them sometimes as integers, I stored them as octal, I stored them as hexadecimal, and now I'm trying to read it back out, but I'm trying to read it back out as a all decimal, but this is what I get. So I entered 15 5 times. So, and then when I read it back out, 15 reads back out decimal as 15, 15 reads back out as integer 15, but the next one I said store as an octal number, so that's base 8. So 15 in decimal corresponds to 13 in base 8. Unsigned int is the same. And this next one, 1-5, store it as a hexadecimal number. Well, 1-5 as a hexadecimal number means 21 as a decimal number. Maybe I show that to you in just a minute. And then I said, okay, display A, B, C, D, and E as hexadecimal numbers. So 15 is F in hex. 15 decimal is F in hex. So now I've interpreted it as a hex number, and so it will output F, F, D, F, and I stored it as a hex 15. It prints as a hex 15. So let me just go over that real quick. My decimal number, which is base 10, is base 10 number, and I'm going to convert it to a octal number, which is base 8. And I'm going to it's hard sometimes to draw on this drawing pad. Base 16 number, which is a hexadecimal number. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry. Voila, I fixed it with a table just for you. Much neater than trying to use my pen. So I inputted 15 as an integer, stored it as an octal or a hex number. So it stores, I have a mistake here. I didn't count. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B. Can't count. More like can't type. So 15 as a decimal number will get stored, if it's in octal, it will get stored as a 21 in octal, and it will get stored in hex as an F. But then when I read it back out as decimal, 15 in 15 right here in octal, if you read it back out as a decimal, would be a 13, and that's what I have right here. Then 21 or 1-5, which I don't have room for down here, but 1-5 stored as a hex number corresponds to, it's down below the end of this chart, would correspond to 21 decimal. So the last little interesting thing I thought about this chapter, and it is a short chapter, is using a scan set, which I thought was a little different. So you can define an array, and I'm giving 9 spaces for this array, and ask the user to enter a string. But when I use this scanf thing, I'm going to allow up to 8 characters to be saved in Z, but I'm only going to look for the characters A, E, I, O, and U. And that's what I'll look for, and I will store the occurrence of these characters in location Z. The interesting thing about this is, though, as soon as you hit a character that's not one of the ones you're searching for, the search will end. I actually put that piece of code in a program. Here, let me get it up. It's more fun to, you don't want to just look at just one example of this to understand it. So I put it in my one program here that I made. You can see I make all my examples here, then I comment them out. And so this is the example that I'm working on now, is this little piece of code. So let me compile that. Unfortunately, the program name doesn't correspond to the one in the book because I just keep modifying to do my examples. But let's do it. Did I save? Yes, I did. Oops. Enter a string. Now remember, I'm searching for A, E, I, O, and U, so I think I'll put E, E, I, O, IIOO FU, didn't mean that, and put that in, but it will find EEIIOO, but it will not, it'll stop because it encountered an F and it won't look for the U. And it'll do up to the first, what did I tell the code to do? Up to the first, I can take 8 characters and store it in Z. So it will search for the first 8 occurrences of any of these characters until it finds a character that's not one of them that it's searching for. So I can't say I've used this a whole lot, but it's kind of a nifty little search thing if you're going through a set of characters. So basically, that's all of Chapter 9. I hope it at least formalized scanf and printf functions. Being very detailed about what the format looks like is going to come into play when we do file read and write operations. It's actually in 2 chapters, but I think I'm going to skip a chapter and skip to the file read write operations. So that's it for this chapter. There's also insignificant homework, so I'll take a look at the My Programming Lab. All for now. Bye.